I would like to talk about where derivatives fail to exist. I have a bunch of functions drawn here, and what I want to do in each one is show you a place where the derivative of that function fails to exist. In this first picture, I'm really thinking about the absolute value example, where we saw the where we saw the derivative did not exist at the origin. And the idea was all the slopes on the left-hand side of 0 are -1, the slopes on the right-hand side are all 1, and I end up with a left-hand side derivative and a right-hand side derivative that are different. And it turns out when that happens, I always get a sharp point, so we call these corners. And that's actually what I see in this diagram too. On the left-hand side of whatever this value is, I'll call it A. On the left-hand side of A, the derivative would be the slope. So as I get closer and closer to A, the derivative is still the slope. On the other side, it looks like my slope is negative but tending towards 0 there. So on one side, I'd have a positive number. On the other side, I would have 0. And again, I have that kind of corner, right? That sharp place. All right, so corners. Slope on the left is different than slope on the right. In this bottom picture, in this first column, I could imagine a secant line. And then to try to talk about the derivative at this point, I could imagine letting this point get closer and closer and closer, right? The idea that h tends towards 0. And if I just get a little closer, I see that my secant line gets steeper, right? They both have negative slopes, but this one's really steep, and even closer, even steeper. It looks like it's trying to become a vertical line. But along the way on this side, all of the slopes were negative. So what I would claim for that vertical line is like my slopes are trying to become minus infinity. They're becoming larger and larger in terms of a negative quantity. All right, on the other side, I have a secant line. And again, I'm getting closer and closer to the vertical line, but all my lines have positive slopes. So on this side, I would say my slopes are becoming infinite. And when this happens, we get that shape that now I've obliterated. We call this one a cusp. And again, the thing it shares with these is it's a sharp point. Sharp points are bad. It turns out they come in two different kinds, corners and cusps. A cusp is like we have a vertical tangent line in the middle, but behaving differently on both sides. And the corners, we just have different slopes on the left and right hand sides. All right, moving on to this picture. If I draw a bunch of tangent lines here, when I get to the middle, it's like the tangent line would need to be vertical, right? And looking at the other side too. And that's really what's happening there. That's a vertical tangent line. Well, that would have an undefined slope. Again, it's kind of like the slope trying to become infinite, but kind of behaving the same way on both sides. So the vertical tangent line. So I have corners, cusps, and then vertical tangent lines. And 1, 2, 3, 4 pictures here of places where derivatives don't exist. But these next 4 all have something in common. They're examples of discontinuities. It turns out that if you have a discontinuity, then you can't have a derivative at that point. So looking at this first picture, the jump discontinuity, I could try to draw a secant line over here that becomes a tangent line, and on that side I might even get a value, but I would definitely get a different value if I tried to go through this point and a point on this side. In fact, it doesn't even look like it makes sense, like I wouldn't even get a tangent line. This is a removable discontinuity, but f of a doesn't, if I call this a, does not exist. Well, I can't calculate a derivative at a if a doesn't exist. My difference quotient definition of derivative at a requires me to be able to calculate f of a. All right, well, here's my removable discontinuity again, but f of a does exist. It's just kind of in the wrong spot, whatever that means. Well, here my secant lines would behave very oddly, and as I get closer and closer to that value there, it's like they would become nonsensically vertical. And here's my wild oscillation, and that's the idea that that function bounces around so much that I wouldn't even be able to draw a secant line. So, by my count, I have 1, 2, 3, 4 kinds of places where a derivative doesn't exist. Corners, cusps, vertical tangent lines, in any discontinuity. Those are the places where a derivative would fail to exist.